Good. So, we looked at last class the force balance and the metal transfer kinetics, right. So, we looked at various forces that aid the metal transfer and the forces which resist the transfer, right. So, what are the forces that aid the metal transfer? Gravity, if it is favorable. Okay. So, if the angle between the arc axis and the vertical, okay, so if it is parallel or 0, then you get the maximum. Okay. So, that means that the downward welding, so you get the gravity influenced favorably for detaching the droplet. Okay. The droplet size also influenced by the force balance. Okay. If the gravity is the major force that controls the detachment, then the globes, the droplets should gain enough mass to maximize the gravitational force, right. And then we looked at the second force, which is plasma drag force or aerodynamic force. Okay. So, which is a function of your shielding gas as well as the process characteristics. Okay. So, that you can play around by changing the velocity, and you can also change by changing the sealing gas. So, the gas which gives the maximum arc core density or plasma jet velocity. So, you will also promote by detachment by making or by inducing the more plasma drag force, right. And then third force, what is the third force? Lorentz force. So, Lorentz force, in most of the cases it aids the detachment, is not it, especially if the Lorentz force is diverging from the tip, that aids the detachment. Okay. And if it converges, then it resists the detachment, right. So, the Lorentz force in most of the welding cases it aids, and Lorentz force becomes rate controlling when the current is increased to beyond critical limit. Okay. So, especially, so when the current is increased, and we also see the change in droplet diameter, okay, from the globular to rippled globular, and then it becomes spray. So, in spray case, in spray transfer case, the Lorentz force is rate controlling, right, and the droplet diameter becomes equal or less than the wire diameter. Okay. So, when you achieve the spray transition, right. And what are the two other forces which resist the detachment? Surface tension and then vapor pressure. So, vapor pressure is created because of the vaporization of the well pool, and the pressure the vapor which is generated, it pushed towards the droplet, and this vapor force generated from this vapor always resist the detachment, right. And the vapor force is also the reason why you have a ripple transfer. Okay. So, globular becomes ripple globular because the vapor pressure pushes the droplet, leading to change in shape, and due to that you also change the magnetic forces inside the droplet, and then the droplet becomes from globular to the shape of a circus buffoon shoe, right. So, we looked at the video as well. So, how the ripple transfer takes place, slightly higher current with high vapor jet force pushing the droplet, right. So, these are the 5 major forces that control the droplet detachment, and we also looked at an example using a 1.2 mm carbon wire. So, how the droplet transfer change as a function of current. Okay. So, we looked at the curve. Okay. So, diameter or transfer frequency as a function of current, right. Now, how does the diameter change? So, you have a larger diameter because at lower current gravity is the major rate controlling, is not it. So, you need to generate enough mass. Okay. So, it decreases like that. Okay. Upon certain current from globular it becomes spray. Okay. So, the transfer frequency increases as a function of current as well. Okay. So, upon certain current the transition becomes from globular or rippled globular to spray, and that current is known as spray transition current. So, most of the GMAW operations are carried out in and around spray transition, so that we promote spray transition, and we also make sure that the transfer is stable. So, if you increase the current further, the spray transfer becomes jetting spray. Okay. So, then there is a possibility of creating spatter and explosion when the droplet is detached because of tremendous increasing Lorentz force as well as the vapor pressure, because when you increase the current, the arc, the current density also increases, is not it, E. So, the heat generated in the arc also increases tremendously. So, you end up generating more heat, and the heat input increases or arc energy increases, because VA by speed is the arc energy, right. So, once the arc energy increases, you also input more heat leading to vaporization, and that can influence the detachment as well. So, if you increase the current much beyond spray transition, so jetting spray on or even further rotating jetting spray or even explosive transfer can take place. So, for the most stable operations, the GMAW welding is generally carried out in and around spray transition current. Okay. So, that is the very important the window we operate. So, when you design a welding procedure specification WPS, so one of the factors which actually we consider is the spray transition and what current for a given wire diameter the spray transition is observed. Okay. And then we play around the other parameters. Say for example, if you want to control the heat input, so we can also play around with the shielding gas, or you can also play around with the arc length, wire feed rate, and so on and so forth, right. It is clear. So, the ideal transfer is spray transition. So, when the current is in and around spray transition, you get an ideal transfer in spray mode where the droplet diameter is almost equal to the filler diameter. Okay. So, that transfer is known as drop transfer. Okay. So, this drop transfer happens just above the spray transition, where the droplet is transferred the diameter equal to the filler wire, and this is considered ideal transfer mode, because and you also increase the productivity by achieving the spray, and the droplet becomes very stable and it is not deflected. And if you have ripple globular or jetting spray, so the your droplet transfer is deflected to the other directions than the arc central. So, when you achieve a drop transfer, you transfer a droplet precisely at the arc center, okay, as well as the diameter equal to the filler wire with a very good transfer frequency. So, this drop transfer is considered the best transfer mode. This is spray because it is transferred continuously, and generally happens just above the spray transition current. So, once you achieve such a transfer, and this is the best transfer mode you can have. Okay. So, this is known as drop transfer spray, drop spray transfer, where the droplet diameter is equal to the filler diameter. So, it happens in such a way that, so you have a droplet molten and then you form a neck. Okay. So, when the droplet, the transfer forces succeed the detachment forces, and droplet is getting detached by forming a neck, because it is overcoming a surface tension and the vapor force. So, you form a neck and then droplet is detached as a free flight with a diameter equal to the filler diameter, and this happens continuously in a spray mode. So, if you have jetting spray, then the droplet will be detached, will be attached to the other droplet is coming out, is not it. So, then you will have a continuous stream of a molten droplet transferred, right. And if that is the case, and you also create enormous the magnetic field inside the droplet, and you would see the droplet, once you achieve the jetting spray, the transfer, the spray would be oscillating or sometimes you are rotating because of the influence of magnetic field and Lorentz force, and that is not advisable, because then that will lead to spatter, and the moment the liquid metal more surface area is exposed to arc, you also vaporize, right, and that would lead to the increased fume generation or the smoke generation, and then you will also have a spatter. So, the moment you create an enormous amount of Lorentz force, the vapor can also explode, the droplet can also be exploded, right. So, this is the ideal transfer you would get, which is in spray mode, where the droplet diameter is equal to the fill away diameter, right, and this can be achieved in most of the cases by using pulsing. Okay. So, the pulsed current promotes the drop transfer. Okay. So, we will come back to that later, but we will look at the video how this transfer happens in real life. Okay, see that. So, I am giving a pulse here, and every pulse there is a droplet detached, and this is recorded using high speed camera. So, what you see over here is it happened within a second, the entire video, even less than a second. So, you transfer as much droplet as possible. So, when you are recording with high speed within frames of 10,000 frames per second, okay, so you would see a number of droplet detached. So, you see that there is a neck formation. Okay, so, the neck formation is very critical here. Okay, so, the moment the droplet is formed, it is pulled down by the Lorentz force plus the gravity and as well as the plasma jet force. So, droplet once it forms, the surface tension is trying to keep the droplet, is not it? That is why you form the neck. Okay, the force, so the aiding force should resist the surface tension. So, this neck formation is due to the surface tension, which is trying to keep the droplet intact with the wire. Okay. So, once the neck is formed, obviously the increased Lorentz force would pull the droplet down, right. So, this is the drop spray. Right, and this is the most preferred the metal transfer mode in JMAW, where you have a spray mode. So, you are not compromising the productivity, and also the droplet is extremely stable and it transferred to the workpiece at a right angle, which is actually beneficial, because then you can also control the metal transfer such a way that you will have a less spatter. Yes, it is clear. So, compared to these, and if you have a spray, a jetting spray and the global ripple transfer, and you have so material will be, the droplet will be transferred to much larger area. You see here, this is sort of the diameter when it is transferred much smaller than the fill-over diameter, is not it? And it is also continuous spray, right. So, this is what we know as jetting spray. You see that the droplet is transferred to a varying angle, is not it? Same here when you transfer in globular or rippled globular, and you also form lot of spatter. So, because of a huge mass, when it is exposed to the arc column pressure, and you also create a magnetic field because of the Lorentz force that are contained in the droplet, and you may expect the droplet to explode sometime, causing spatter, right. So, whereas in jetting spray you have a high productivity because the transfer rate is much higher, but the stability of the process is affected because of the exceeding forces that aids the droplet transfer, which are Lorentz force, right, and then plasma jet force. Yes, it is clear. So, the most preferred the transfer mode is the drop spray mode, where you transfer the droplet, the diameter similar to the filler wire, right, and this happens just above the spray transition. Okay. So, in order to achieve the spray transition, and you will have to have the current increase to certain amount, is not it? So, you will have to increase the current to a certain amount, say about 200 amperes in this case. And if you have a constant current, so then you will have to give about 200 amperes. But when you are doing pulsing, and you can also achieve this mean current by giving a pulsing where the I mean will be much lower. Okay. For example, in a constant current mode, if the spray transition happens at 200 I mean current, and you can also achieve the spray transition when you are giving pulsing. Okay, you can pulse between 350 amperes to say minimum say 20 amperes on this time, whereas in this case the mean current will be much lower than 200 amperes in pulsing, but still you may achieve this spray transition, is not it? Because so when you are giving one pulsing, and during this pulsing the current goes 350 amperes IP, the peak current, is not it? So you would immediately melt the droplet, and droplet can be detached because of the increasing in Lorentz force, right? Whereas in this case the current is constant, where in I mean in constant current is 200 amperes, whereas in here in 150 amperes in the pulsing case you can achieve a droplet transfer in drop spray mode. So that is why pulsing is always advantageous, okay, because you can achieve the spray transfer in much lower mean current, right. Again we will see when in detail when you are looking pulse GMAW. So right now what I want to say here is, in order to promote the spray transfer, we will have to increase the current above spray transition current, okay, and the spray transition current for constant current GMAW, whereas in pulse current GMAW the mean current will be different. In pulse GMAW the mean current will be much lower to achieve this spray transition, right. Is clear? Any questions so far? Okay, good. So the varying as a function of diameter, the spray transition current also changes, okay. So for example, for a given shielding gas, for 1.2 mm filler wire, that is the most commonly used filler wire diameter. So in this case plain carbon steel wire 240 is the spray transition current, right, for in a constant current configuration. And if you are using pulsing, it can happen 200 amperes, much lower than what you have it in a constant current mode, right. And you also see by increasing carbon dioxide what happens, spray transition current increases. Why? Because the arc energy, right, the heat in arc, the heat energy in arc is decreasing, right, because of increasing carbon dioxide. So you need to increase the current to compensate the decreasing in heat distribution in the arc, right. Again it comes from the physics of shielding. It's clear? Good. So when you increase the current even further from drop spray becomes streaming spray. So streaming spray is characterized by so much smaller in diameter of the filler which is transferring to the workpiece, and you have a continuous small diameter overlapping leading to a complete spray, continuous spray going to the workpiece. It happens in very high current, generally in a 1.2 mm plain carbon steel more than 300 amperes, and then leading to a partial molting of the tapering of the electrode tip, and then you get a very fine droplet transferring. Okay, so this happens because of significant increasing Lorentz force, right, because of very high current. Okay, so generally it happens in high resistance and small diameter filler, okay, because then you also promote the effect of Lorentz force. And once you have the streaming transfer, it will also cause well put turbulence. So obviously you have enormous amount of liquid going, like in a bucket, open a tap at high speed, and in another bucket you open a bucket in a drop, which would have a maximum turbulence. So obviously when you open that tap fully and you see the enormous turbulence in the bucket of water, right. So because of that the well pool stability is also decreasing, right. You also affect the fluid flow. Your fluid flow is not controlled, then you also have influence of this in the subsequent nucleation, the microstructure development as well, right. It's clear. So, we look at drop transfer. So, main characteristic I have just listed down, the drop transfer is the which is ideal transfer mode, isn't it? It occurs very narrow range just above the spray transition, okay. And so from the video what you saw, it is characterized by a conic neck at the tip and diameter is equal to the Filloy diameter, okay. So, you see the droplet is suspended by the surface tension, okay, and then detached, right. And in this mode we can also achieve a high droplet transfer rate, okay, with very low spatter. So, if you look at 1.2 mm carbon steel wire, it happens at 250 to 270 amperage with argon 5% CO2. So, you see the velocity, droplet velocities of 117 mm per second we can achieve, okay. So, in order to achieve this transfer, the parameters should be closely controlled, okay, 250 to 270 amperes. So, that is the range you need to operate in a constant current. In a pulsing it is promoted because we can play around, each pulse you can make one droplet transfer, okay, like a video I showed you, right. So, what is the ideal transfer is a drop spray transfer.